Welcome to lecture 26. The topic is we want to show that rings of integers are Dedekind domains. So this week we've been talking about Dedekind domains. So now we want to give some class of examples of Dedekind domains that goes back to the first week. So we want to show that rings of integers are Dedekind domains. Okay, so there are two settings that we are primarily interested in. One is called the number field setting, and the other is called the global function field setting. And so what we have in the number field setting is we have a number field k over q, which just means we have a finite field extension of q. And inside q we have integers z, and then we have ok, which is the integral closure of z in k. And in the global function field setting, the base field is fp brackets t, and once again we have a finite field extension, and in this case, since the residue or the characteristic is p, we require the extension to be separable. So we want a finite separable field extension. And inside that we have the polynomial ring fpt, and just as earlier we look at the integral closure. So ok again is the integral closure of the polynomial ring in one variable over fp in k. Okay, so the theorem in both these settings OK is a Dedekind domain. And just as a reminder, that means that OK satisfies three properties. So OK is integrally closed in its fraction field. OK is a Noetherian ring. And if you take any non-zero prime ideal, that's maximal. Okay, so we need to show that OK has these three properties. So the first property is a direct consequence of something that we proved in the first week, the second lecture, that was corollary 4. We've showed that if you take integral closures, then that's integrally closed in its fraction field. So this was week 1, lecture 2, corollary 4. And the fact that OK is Noetherian was also something we covered in the first week. So just as a reminder, this was proposition 8, week 1, lecture 4. So what we showed in that proposition, the setting was the following. So we had a finite separable field extension again. L over f, let's say. And let's say that the degree of this field extension is n. Inside f, we found a PID A, such that the fraction field of A equals f, and then B was the integral closure of A in L. So under this hypothesis, what we showed was that, so then we showed that B is a free A module of rank n. And then if you apply this to our setting, we get, so the setting is that L equals K, and then depending on whether you're in the function global function field setting or the number field setting, F is Q or FPT, and then A, again depending on the setting, it's either Z or the polynomial ring over Fp in one variable, FPT, and then B is the integral closure of A in K. So applying this result to our setting, we get that OK is a free A module with rank n. Okay, and so again, how is this applicable to us? So this means that every ideal I of OK is in fact a submodule, a Z submodule of OK, and so if you apply the structure theorem for PIDs, we get that the rank of I as a module is less than or equal to n, since the rank as A module of OK equals n, and we have that I sits inside OK as A module. Okay, so in particular, that I is finitely generated as A module itself, and since A sits inside OK, we have that I is finitely generated as an OK module. This was true for any ideal I of OK, and so thus this shows that OK is Noetherian. Okay, so in particular this proves second property that OK needs to satisfy, in particular that it's Noetherian. So this proves theorem 61 part 2, and now the third part is remaining. So to prove the third part, we will prove a following result, which can be viewed as a strengthening of the going up or the lying above theorem. So we prove the following: strengthening of the lying above theorem. So this is proposition 62. So suppose you have an integral extension of domains. And so let's draw the diagram. It's A sits inside B, and suppose you take a prime ideal of B, call it beta, and it lies above a prime ideal, say capital P of A. So we have a prime ideal beta inside B, and it lies above P in A, which means that P is of the form beta intersect A, and so P is a prime ideal of A. And so in this setting, then what we have is that beta is a maximal ideal of B if and only if P is a maximal ideal of A. Okay, so let's prove this proposition. Okay, so just note that what this field diagram or this diagram, this commutative diagram, what it tells us is, A sits inside B, and this is an integral extension by the hypothesis of the proposition, and under this inclusion P sits inside beta. So if you pull back beta, you get P. So in particular, beta equals, or P equals beta intersect A. And so what that means is that the quotient A over P sits inside B over beta. So you get this induced injection, and the claim is that the induced injection, this extension, is also integral. And again, why? So you take any element, it's called brackets B, in the quotient B over beta. You just pick a lift B in the ring B, and since the extension A into B is integral, you can find a monic equation over A for B. So choose such an equation. So choose an integral equation satisfied by B over A. So let's say it's B to the n plus A n minus 1 B to the n minus 1 plus so on and so forth A1B plus A naught equals 0. And so here all the coefficients A n minus 1, so on and so forth, A1 and A naught, they all lie in A. And so you have this equation, and you just go modulo beta. And just note that you have these AIs that are in A. So going modulo beta in A is just going modulo P. So just note that beta intersect A is P. So if you take the elements of A and you go modulo beta, that's just the same as going modulo P. So you have brackets B to the n plus brackets A n minus 1 brackets B to the n minus 1 and so on and so forth. Where the coefficients now, the reduced coefficients, they lie in A over P, and you view A over P sitting inside B over beta. And so this shows that this brackets B satisfies a monic equation over A over P. Okay, and so thus the quotient B over beta is integral over A over P, and this proves the claim. Okay, so now we want to use this claim. So now observe that to prove the proposition, what's enough to show? Well, we want to show that beta is maximal in B if and only if, well, let me use symbols, if and only if P is maximal in A. But what you know is that beta is maximal in B if and only if B mod beta is a field and A mod P is maximal in A if and only if A mod P is a field. Okay, so the vertical implications are something that we know. We want to show the horizontal implication, and what we've reduced it to showing is the horizontal implication that B mod beta is a field if and only if A mod P is a field. Okay, so we reduced to showing you have an integral extension A over P into B over beta, and we reduced to showing that B over beta is a field if and only if A over P is a field. Okay, so let's prove the direction. Let's suppose A over P is a field and want to show that B over beta is a field. So what we want to show is that if you take an element in this quotient that's non-zero, you want to show that it has an inverse. So this element has an inverse in the same quotient. So again, we have to use the fact that A over P into B over beta is integral. So you write down a monic equation for this element over A over P, but choose a monic equation that has minimal degree. Okay, so let's say it's of the form brackets B to the n, A n minus 1, brackets B to the n minus 1, and so on. And here are the coefficients they belong to A over P, and in this case by hypothesis this quotient is a field. So we assume that we're proving the direction where we assume that A over P is a field, and we want to show that if you have an integral extension where the base is a field, then B over beta is also a field. And so observation, I've chosen this monic equation to have minimal degree, and my observation is that because of that the constant term A naught has to be non-zero. Again, why? If the constant term was 0, and then what happens to this equation? You have that the constant term vanishes, and now if you just factor brackets B, you get brackets B to the n minus 1 and so on and so forth equals 0, and this equality is taking place in B mod beta. Now since by assumption beta is a prime ideal, I don't know if it's maximal or not, but by assumption it's a prime ideal in B, the quotient has to be an integral domain. And so if you multiply two elements of an integral domain and they're 0, then one of the elements has to be 0. But by assumption, since brackets B is not 0, we have that the remaining term must be 0. But now observe that this gives us a monic equation. This gives us a monic equation over A mod P. That's satisfied by brackets B. But this monic equation has degree n minus 1, and so this contradicts the minimality of n. Okay, so the only possibility is that our observation is correct, that this constant term is not 0. So the constant term could not have been, if the constant term was 0, we would arrive at a contradiction. So the only possibility is that our observation is correct. So thus, the constant term is not 0 in A mod P. And since A mod P by hypothesis is a field, the inverse of A naught, brackets A naught, belongs to A mod P. Okay, so once again, just playing around with this monic equation. So let's play around with this monic equation and see what we get. So I just pull the constant term over to the other side, and I get, and if I factor out the b, I get brackets b times brackets b to the n minus 1 plus brackets a minus 1 brackets b to the n minus 2, and so on and so forth, all the way up to brackets a1. And since I can multiply by the inverse of a naught, what I get is brackets b multiplied by minus brackets a naught inverse times this expression out here. That equals 1. And so if you look at this expression inside the brackets, this expression gives us the inverse of brackets b, and this expression is a polynomial expression. It's polynomial in B, where the coefficients are in A over P, and so this expression belongs to B over beta. Okay, so we produce an explicit inverse for brackets B, and so thus brackets B, which is a non-zero element of B over beta, is invertible in B over beta, and so we've shown that if P is maximal in A, then beta is maximal in B. Okay, now for the other direction. So suppose that B over beta is a field, and what we want to show is that A over P is a field. And again, for the sake of contradiction, suppose that A over P is not a field. Well, if it's not a field, it's a domain, and it will have a non-zero maximal ideal. You know, if the only maximal ideal was 0, then it would be a field. So A over P has a non-zero maximal ideal. Call it Q. So again, just drawing the diagram, we have A over P sits inside B over beta, and we have little q, which is a prime ideal of A over P. And now to this setup, I'm going to apply the lying about theorem. So this was done in lecture 6. So we apply the lying about theorem to the integral extension. So by applying lying about theorem to the integral extension, say A over P inside B over beta. So we get a prime ideal, say capital Q, inside of B that lies above little q. So I have this. So the lying about theorem gives me a prime ideal capital Q inside B over beta. So we have this sort of commutative diagram, and so again, in particular, Q intersect A over P equals little q. Okay, but by hypothesis, so our hypothesis is that B over beta is a field. So since B over beta is a field, the only prime ideal of a field is the zero ideal. So this big Q must be the zero ideal, and so if you just intersect the zero ideal with A over P, you should get back the zero ideal in A over P, but by assumption little q was not 0. Okay, so this is the contradiction. So thus the only possibility is that A over P is a field, and so thus we've shown that if beta is a maximal ideal of B, then P is a maximal ideal of A. Okay, and so we've shown both directions of the proposition, and so this completes the proof of the proposition. Okay, so now how to use this proposition to complete the proof of the theorem, theorem 61. And this was the third part that was remaining. So again, just as a reminder, we had these two settings. We had this number field setting, so we had this finite extension, and we looked at OK, which was the integral closure of Z. In K, and so we have a prime ideal, let's say beta inside OK, and then we can look at the prime ideal below, which is beta intersect Z. And so you can do the same game in the global function field setting. Where we have Fp brackets T, we have a finite separable extension. We have the polynomial ring in one variable, and we have the integral closure of this polynomial ring in K. And just as earlier, we take a prime ideal of OK, and then let P be the prime ideal below, that's given by beta intersect Fp brackets T. So again, here OK is the integral closure of is one variable polynomial ring in K. And again, what we're given is beta, which is a non-zero prime ideal of OK. And what we want to show is that beta is maximal, and by applying the previous proposition, proposition 62, it's enough to show that the prime ideal P below that P is a maximal ideal of Z or Fp brackets T. Okay. But since Z and Fp brackets T are PIDs, so we know that all non-zero prime ideals of PIDs are maximal. It's enough to show. Well, I already know that P is a prime ideal, so it's enough to show that P is non-zero. Since we know already that P is prime, and for PIDs, non-zero prime ideals are maximum. Okay, so now you take an element alpha in beta, so that this be a non-zero element, and again just as earlier, consider a monic equation satisfied by alpha over A. So A could be, so A is this PID that could either be Z or Fp brackets T. And just as earlier, you choose the degree to be minimal. So you have alpha to the n plus an minus 1 alpha to the n minus 1 and so on, plus alpha a1 alpha plus a naught equals 0, where these ai's a1 a naught, they're all in A, and since alpha is not 0, just as earlier, the minimality of n forces the constant term a naught to be not 0. Okay, but what's a naught? Again, if you just solve for a naught, you get that a naught is minus, move everything to the other side, you get alpha to the n plus a n minus 1 alpha to the n minus 1 plus so on and so forth plus a1 alpha. And if you look at this expression again, it's a polynomial expression involving alpha. So with no constant term, and the coefficients are in A, and so now since alpha belongs to Q, we get that this the constant term a naught also belongs to Q, but the constant term a naught belongs to A, so it belongs to beta. I call this prime ideal beta and not Q. So this constant term belongs to beta intersect A, which is nothing but P, and we've already seen that the minimality assures us that A naught is non-zero, So we produced a non-zero element A naught in P. So this shows that P is maximal in A. So it's a maximal ideal in A. So A could either be Z or Fp brackets T. And so this shows that beta is a maximal ideal in OK if so if beta is a non-zero prime ideal of OK. Okay, so this proves the third part of the theorem, third part of theorem 61, and so this completes the proof of theorem 61 that OK is a Dedekind domain. Okay, so I'll end this lecture by stating but not proving the structure theorem for finitely generated modules over Dedekind domains. So if you've taken a course in abstract algebra involving ring theory and module theory, you've seen the structure theorem for finitely generated modules over PIDs. So what I'm about to state is a generalization of that, but unfortunately we don't have time to go over the proof, so I'll just give the statement. So we'll end with we'll end this lecture with the statement but no proofs for the structure theorem for finitely generated modules over Dedekind domains. Okay, so what's the setting? So you start with a ring R, which is a Dedekind domain. And suppose M is a finitely generated R module. So I want some sort of structure theory for M. And just as in the structure theory for PIDs, you look at the torsion submodule, which I call M tor. It's a set of all elements in M such that it's annihilated by some element of the ring that's not zero. And so it turns out the set is in fact an R submodule of M. So it's called the torsion submodule. So we have this inclusion M tor inside M, and furthermore if you take the quotient M over M tor, this turns out to be a torsion free. If we take the quotient, it has no more torsion. The torsion submodule of the quotient is 0. So what we say is that the quotient is a torsion free R module. So the statements of the structure theorem are the following. So there exists an isomorphism which is not canonical in some sense. So it's a non-canonical R module isomorphism. So M is isomorphic to the torsion submodule plus the quotient. So it has a torsion part and some sort of non-canonical torsion free part. And so the question about determining the structure of M boils down to structure of determining the torsion free part and the torsion part. So one question then is, what is the structure of M tar and the quotient M modulo M tar. Okay. So theorem 64 is, the statement is similar to what you know about the structure theorem for finitely generated torsion modules over PIDs. So you have this invariant factor form. So suppose that a module is a finitely generated torsion R module, then there exist ideals I1, I2, in of R such that the module M is isomorphic to R mod I1 plus R mod I2 and so on and so forth, R mod In, with the property that I1 sits inside I2, sits inside I3 and so on up to In. Okay, so if you can choose these ideals to satisfy the property that they include one inside the other, then these ideals Ij are actually uniquely determined by M, and these are called the invariant factors of M. Okay, and just as for structure theorem for torsion finitely generated modules over PIDs, we also have an elementary divisor form. So once again, suppose M is a finitely generated torsion R module, then there exist prime ideals P1, P2, so on up to Pn, and positive integers E1 and E2 all the way up to En, such that the module M is isomorphic to R mod P1 to the E1, R mod P2 to the E2, and so on and so forth, R mod Pn to the En. And so these Pi to the Eis, these are called the elementary divisors of M. And they are also uniquely determined by M up to reordering. Up to permutation. Okay. And so the last part of the structure theorem is for torsion free modules. So suppose M is a, let's say, non-zero finitely generated and torsion free R module. Then there exists a positive integer R and an ideal I of R such that M, this torsion free module, this non-zero finitely generated torsion free module is isomorphic to R minus 1 copies of the ring direct sum with I. Okay. So this, the integer r is called the rank. So this integer r is uniquely determined by m. It's called the rank of m. And so this ideal I is also almost uniquely determined by m, so it's well defined, or it's only uniquely defined up to its image. Well, it's an ideal, so you can look at its image in the class group. So it's well defined, or it's uniquely determined up to its image in the class group. So reminder, CL of R is the class group of R. It's the quotient of the fractional ideals modulo the principal fractional ideals. And so this class of I in the class group, this equivalence class is called the Steinitz class of I, let's say, or M. And so another fact is that two finitely generated Gaussian free modules are isomorphic if and only if they have the same rank and the Steinitz class. Okay. So this completes the proof of the structure theorem for finitely generated modules over Dedekind domains. So maybe just as an exercise, to get a grasp of these statements, what you can try to check is just compare the structure theorem. So you compare with the structure theorem for finitely generated modules over PIDs, and just ask yourself, are the statements that I wrote down, so are these statements generalizations of the structure theorem that you already know? Okay, so that concludes the topic of Dedekind domains. Thank you.